Lecture 4, Systems of More Than One Particle. It's a lazy, warm evening. Lenny and George are lying in the grass looking up at the sky. Tell me about the stars, George. Are they particles? Kind of, Lenny. How come they don't move? They do, Lenny. It's just that they're very far away. That's an awful lot of them, George. Do you think that guy Laplace could really figure them all out? Systems of particles. If, as Laplace believed, natural systems are composed of particles, then the laws of nature must be the dynamical laws of motion that determine the motion of those systems of particles. Again, Laplace, on the quotes, an intellect which at a certain moment would know all forces and all positions. Close quotes. What is it that determines the force on a given particle? It is the positions of all other particles. There are many types of forces, such as friction, the drag force exerted by the wind, and the force exerted by the floor that keeps you from falling to the basement, that are not fundamental. They originate from the microscopic interactions between atoms and molecules. The fundamental forces are those that act between particles, like gravity and electrical forces. These depend on a number of things. Gravitational forces between particles are proportional to the product of their masses, and electrical forces are proportional to the product of their electric charges. Charges and masses are considered to be intrinsic properties of a particle, and specifying them is part of specifying the system itself. Apart from the intrinsic properties, the forces depend on the location of the particles. For example, the distance between the objects determines the electric and gravitational force that one particle exerts on another. Suppose that the locations of all the particles are described by their coordinates x1, y1, z1 for the first particle, x2, y2, z2 for the second particle, x3, y3, z3 for the third particle, and so on up to the last or the nth particle. Then the force on any particle is a function of its location as well as the location of all the others. We can write this in the form vector Fi equals vector Fi under bracket curly bracket vector r. What this equation means is that the force on the ith particle is a function of the positions of all the particles. The symbol curly bracket vector small r stands for the collective location of every particle in the system. Another way of saying this is that the symbol represents the set of all position vectors. Once we know the force on any particle, for example particle number 1, we can write Newton's equation of motion for that particle. For example, vector F1 and curly bracket small r equals m1 times vector a1, where m1 and vector a1 are the mass and acceleration of particle 1 respectively. When we express the acceleration as the second derivative of the position, the equation becomes vector F1 curly bracket r1 is equal to m1 double derivative of vector r1. In fact, we can write such an equation for each particle. Like for example, vector F1 r equals m1 double derivative of r1. Also vector F2 curly bracket vector r equals m2 times double derivative of r2 and so on till nth particle. Or in condensed form, vector Fi curly bracket small r equals mi times the second derivative of ri. We can also write these equations in the component form. Vector fx I curly bracket x equals mi times the double derivative of xi and correspondingly for other x's. In this set of equations, fxi, fyi and fzi mean the x, y and z components of the force on the ith particle, and the symbols curly bracket x, curly bracket y and curly bracket z represent the sets of all the x coordinates, all the y coordinates and all the z coordinates of all the particles. This last set of equations makes it clear that there is an equation for each coordinate of every particle, which would tell Laplace's vast intellect how every particle moves if the initial conditions were known. How many equations are there in all? The answer is 3 for each particle. So if there are n particles, the grand total is 3n equations. The space of states of a system of particles. The formal meaning of a state of a system is everything you need to know with perfect accuracy to predict its future given the dynamical law. Closed quotes. Recall from lecture 1 that the space of states or state space is the collection of all possible states of the system. In the example of lecture 1, the state space was typically a discrete collection of possibilities, capital H or capital T for the coin, 1 through 6 for the die, and so forth. In Aristotelian mechanics, assuming that the forces on an object are known, the state is specified by simply knowing the location of the object. In fact, from Aristotle's law, the force determines the velocity, and the velocity tells you where the particle will be at the next instant. But Newton's law is different from Aristotle's. It tells you the acceleration, not the velocity. This means that to get started, you need to know not only where the particles are, but also their velocities. Knowing the velocity tells you where the particle will be. All of this means that the state of a system or particle consists of more than just their current locations. It also includes their current velocities. For example, if the system is a single particle, its state consists of 6 pieces of data, the 3 components of its position and the 3 components of its velocity. We may express this by saying that the state is a point in a 6-dimensional space of states labeled by the axes x, y, z, vx, vy, and vz. Now let's consider the motion of the particle. At each instant of time, the state is specified by the values of 6 variables: xt, yt, zt, vxt, vyt, and vzt. The history of the particle can be pictured as a trajectory through the 6-dimensional state space. Next, consider the space of states of a system of n particles. To specify the state of the system, we need to specify the state of every particle. This obviously means that the space of states is 6n dimensional, 3 position components and 3 velocity components for each of the n particles. One may even say that the motion of the system is a trajectory through a 6n dimensional space. But wait, if the state space is 6n dimensional, why is it that 3n components in equation 1 are enough to determine how the system evolves? Are we missing half the equations? Let's go back to a system of a single large particle with specified forces and write Newton's equations, using the fact that acceleration is the rate of change of velocity. M times the time derivative of vector v equals vector f. Since there is no expression for the velocity here, let's add to this another equation expressing the fact that velocity is the rate of change of position. Time derivative of position vector r equals vector v. When we include this second equation, we have a total of 6 components that tell us how the 6 coordinates of the state space change with time. The same idea applied to each individual particle gives us 6n equations governing the motion through the space of states. Mi times the time derivative of velocity equals the force F, and the time derivative of position vector is Vi. Thus, in answer to the question posted above, we were missing half the equations. Wherever you happen to be in the 6n dimensional space of states, equation 2 tell you where you will be next. They also tell you where you were an instant ago. Thus, equations 2 are suitable dynamical laws. We now have our 6n equations for n particles. Momentum and phase space. If you are struck by a moving object, the result depends not only on the velocity of the object, but also on its mass. Obviously, a ping pong ball at 30 miles per hour, about 13 meters per second, will have much less of a mechanical effect than a locomotive moving at the same speed. In fact, the effect is proportional to the momentum of the object, which for now we shall define as the product of the velocity and the mass. Since the velocity is a vector, so is the momentum, denoted by the letter p. Thus, momentum pi equals the product of mass mi times velocity vi, or vector p equals mass times vector velocity. Since velocity and momentum are so closely linked, we can use momentum and position instead of velocity and position to level the points of the state space. When the state space is described this way, it has a special name, phase space. The phase space of a particle is a 6-dimensional space with coordinates xi and pi. See figure 1. Figure 1, a point in phase space. Why didn't we call this space configuration space and the new term phase space? The reason is that the term configuration space is used for something else, namely the 3-dimensional space of positions. Just the RIs. It might have been called position space. Then we could have said On the course, position space plus momentum space equals phase space. In fact, we do say that, but we can also use the term configuration space interchangeably with position space. Therefore, the slogan is configuration space plus momentum space equals phase space. You may wonder why we go to the trouble of replacing the intuitive concept of velocity with the more abstract concept of momentum in describing the state of a particle. The answer should become clear as we develop the basic framework of classical mechanics in later chapters. For now, let's just re-express equations 2 in terms of momentum instead of velocity. To do so, we first note that m times the time derivative of the velocity vector v is nothing but the time rate of change of momentum. That is the dp by dt, or in the condensed dot notation, mass times the time derivative of velocity vector equals the time derivative of momentum vector p. The full set of equations becomes pi dot equals to fi and curly bracket small ri, or time derivative of position vector ri dot equals momentum vector pi divided by mass. This simple, elegant set of equations is exactly what Laplace imagined the laws of nature to be. For each coordinate of phase space, we have a single equation to tell you how it changes over an infinitesimal interval of time. Action, reaction, and the conservation of momentum. The principle of the conservation of momentum is a profound consequence of abstract general principles of classical mechanics that we have yet to formulate, but it can also be understood at an elementary level from the Newton's third law of motion. For every action, there is an equal and opposite reaction. The simplest way to think of the third law is to suppose first that particles interact in pairs. Each particle j exerts a force on each other particle I, and the total force on any particle is the sum of the forces on it exerted by all the other particles. If we denote the forces on particle I due to the particle j by the symbol Fij, then the total force acting on the particle I is total force F vector I equals the summation j Fij. The left side represents the total force on particle I, and the right side is the sum of the forces acting on I due to all the other particles. Newton's law of action and reaction is about the force between pairs of particles Fij. What it says is simple. The force due to one particle j on another particle I is equal and opposite to the force due to particle I acting on particle j. As an equation, the third law says that for every I and j, vector Fij equals minus vector Fji. Let's rewrite the first of equations 3, plugging it in equation 4. Time derivative of position vector pi equals summation j force vector Fij. In other words, the rate of change of the momentum of any particle is the sum of the forces due to all the other particles. Now let's add up all these equations to see how the total momentum changes. Summation I pi equals summation I summation j vector Fij. The left hand side of this equation is the sum of the rates of change of all momenta, the plural of momentum. In other words, it is the rate of change of the total momentum. The right hand side of the equation is 0. That's because when you write it out, each pair of particles contributes 2 terms, the force on I due to j and the force on j due to I. The law of action and reaction, equation 5, ensures that these cancel. Thus, we are left with an equation that we can write in the form the time derivative of the summation of vector pi equals 0. This equation is precisely the mathematical expression of the conservation of momentum. The total momentum of an isolated system never changes. Let's consider the 6n-dimensional space of p's and x's. At every point, the entire collection of momenta are specified, so it follows that every point in the phase space is partially characterized by a value of the total momentum. We could go through the phase space, leveling each point with its total momentum. Now imagine starting a system of particles at some point. As time evolves, the phase point sweeps out a path in phase space. Every point on the path is leveled with the same value of total momentum. The point never jumps from one value to another. This is entirely similar to the idea of a conservation law that we explained in lecture 1.